Hey everyone, and welcome. Today, we're going to peel back the curtain on a hidden world that's happening all around you every single second. We are going to crack the secret language of chemical reactions. So let's jump right in. So let's kick things off with a little puzzle for you. Picture this. You've got a pizza in the oven, right? The cheese is getting all bubbly, the crust is turning that perfect golden brown. At the same time, you've got a slice of apple on the counter that's starting to turn brown. What in the world do those two things have in common? You got it. It's all about chemistry. They're both prime, everyday examples of a chemical reaction taking place. And these transformations, they aren't magic. They're predictable changes. And today, we're going to learn exactly how to spot them and understand their secret code. Okay, so first things first. How do we even know when a chemical reaction is actually happening? Let's dig into the telltale signs, the clues that chemistry leaves behind for us to find. So, what are these clues? Well, first, look for a change in temperature. You can't miss the heat coming off a campfire, right? Second, a change in color. Kind of like how a shiny new chain on your bike will eventually get that reddish tint of rust. Third, a change in odor. We all know that terrible sulfur smell of a rotten egg. Yikes. Fourth is the formation of gas bubbles, like when you plop an antacid tablet into a glass of water and it starts fizzing. And finally, the formation of a solid. This one's cool. Sometimes you mix two totally clear liquids and bam, a cloudy solid suddenly appears. We call that a precipitate. See any of those? Chances are you're looking at chemistry in action. So once scientists figured out how to spot these reactions, they ran into another problem. How do you describe them to someone else? How could you share what you found with another scientist halfway across the world without writing a huge, complicated paragraph every single time? They needed a universal code, a shorthand. And at the very heart of this code is a really simple but super powerful idea. A chemical reaction isn't about making brand new atoms out of nothing. It's about taking the atoms you already have and just rearranging them. Think of it like having a big pile of Lego blocks. You can take apart a car and use those exact same blocks to build a spaceship. The pieces are the same, but what you built is totally new. And here's the key part of the code: understanding the before and the after. On the left side of any chemical equation, you've got your starting ingredients. We call those the reactants. Then, on the right side, you've got what you end up with when it's all said and done. Those are the products. That's it. Reactants on the left, products on the right. Easy. And this pretty much says it all. The chemical equation. It might look intimidating, but it's not meant to be scary. It's actually the chemist's ultimate shortcut. It's a super condensed, universal language that tells you exactly what ingredients you started with and exactly what you made. But here's the thing. You can't just write down whatever you want. There is one law, one absolutely unbreakable rule that governs every single chemical reaction in the entire universe. And this is it, the law of conservation of mass. All it really means is that you can't just lose atoms, and you can't just create new ones out of thin air. Every single atom you start with in your reactants has to be there, somewhere in your products. Nothing ever really disappears. So how do we make sure our equations actually follow this universal law? Well, we balance them. Let's go back to our Lego blocks. If you started with 10 red blocks and 5 blue blocks, your final spaceship has to have exactly 10 red and 5 blue blocks, right? They're just in different spots. Balancing an equation is just the accounting. It's us doing the math to prove that every single atom we started with is still there at the end. All right, so we can spot reactions, and we can write them down. But there are millions, literally millions of possible reactions. It'd be impossible to memorize them all. So chemists did what all good scientists do. They started putting them into groups. They started organizing. But why, though? Why bother putting them into different categories? What's the point of classifying all these different reactions? It comes down to one incredibly powerful reason: prediction. See, if you can identify what type of reaction you're looking at, you can make a really good guess about what the products are going to be, even if you've never seen that exact reaction before. It's like knowing the rules of the game before you play. So, let's meet the main families. Think of this like a family tree for chemical reactions. We're going to check out the 4 major types that cover the vast majority of reactions you're ever going to run into. First up, we've got the synthesis reaction. This is the getting together reaction. You take 2 or more simple things, you combine them, and they form one single, more complex compound. Think A plus B comes together to make AB. This is how we create all sorts of new materials, everything from plastics to medicines. Next is the total opposite: decomposition. This is the breaking apart reaction. You start with one complex compound and it splits apart into its simpler pieces. This is literally how an airbag in a car works. A chemical inside rapidly decomposes, creating a burst of nitrogen gas that inflates the bag in a fraction of a second. So AB breaks down into A and B. Now for the next couple of branches on our family tree, the replacement reactions. These are all about atoms and compounds, well, swapping partners. You can almost think of it like a big chemical square dance. In a single replacement reaction, you have one lonely element that comes along and cuts in, kicking another element out of a compound so it can take its place. This is actually a big part of how batteries work. One metal replaces another, and that swap creates the flow of electricity. Just one element switching things up. And then you've got a double replacement. Here, you have two compounds that meet, and they basically just trade partners. The first part of one compound pairs up with the second part of the other, and vice versa, making two brand new compounds. This is what's happening when you take an antacid to settle your stomach acid. And this slide makes it super easy to tell them apart. Just look at what you start with. For single replacement, you see the pattern one lone element plus a compound. But for double replacement, you're starting with two different compounds from the get-go. By just looking at your ingredients, you can pretty much predict what kind of dance is about to happen. So there you have it, the basics of chemistry's secret language. You now know the signs of a reaction, you understand the unbreakable law that governs them all, and you can recognize the key family patterns. The whole world is basically one giant laboratory. Now that you have the code, what are you going to spot? The next time you cook a steak or see rust on a fence, you'll know what's really going on. You've got the manual. Now go explore.